Uranium often stirs up a great deal of fear, and it's easy to see why. Its link to atomic bombs and nuclear power plants isn't exactly the kind of introduction that puts it in a favorable light. Yet, at the same time, there's an undeniable allure that sparks intense curiosity about this metal. Sitting at number 92 on the periodic table, uranium has 92 protons and 92 electrons, showcasing its atomic complexity. It's surprisingly plentiful in the Earth's crust, being 40 times more abundant than silver, for instance. This abundance is because uranium is formed from neutron capture inside supernovas, reminding us of a fascinating truth. Everything on Earth originates from the explosion of stars. Uranium was discovered in the 18th century in Germany, named in honor of the newly discovered planet Uranus at that time. This naming highlights the connection between the discovery of elements on Earth and the exploration of the vast universe around us. This video aims to clarify some misconceptions about uranium, delving into both its alarming aspects and those that pique our interest. Throughout this exploration, we'll gain a deeper understanding of this fascinating element, its history, and how, despite its controversial uses, uranium plays a vital role in our world, from energy generation to medical and industrial applications. Let's embark on this journey together, unraveling uranium's mysteries and discovering what makes it so intriguing. Every uranium atom, defined by its 92 protons, is recognized as uranium regardless of the number of neutrons it has. This specificity is crucial because, although the number of neutrons can vary, the presence of 92 protons identifies the element as uranium. Understanding this principle is key to grasping the concept of isotopes, atoms that share the same number of protons but have different numbers of neutrons. Some of these isotopes are radioactive, meaning they undergo a decay process, emitting particles in the process. These particles can be alpha, beta, either positive or negative, with the latter being an electron or a positron, and gamma, which is a type of electromagnetic radiation. Uranium is known to have 28 isotopes, but only 3 occur naturally: uranium-234, uranium-235, and uranium-238. The numbers following the element's name indicate the total sum of protons and neutrons in the nucleus, and all these isotopes are radioactive. When diving into the topic of radioactivity, a key concept to grasp is half-life, which is the time it takes for half of a radioactive sample to decay. For instance, if we start with 1,000 radioactive atoms, after one half-life, only 500 active atoms will remain. The half-lives of isotopes can range widely, from milliseconds to millions of years, depending on the isotope. Generally, the shorter the half-life, the more radioactive the isotope is. Understanding this concept allows us to appreciate not just the complexity of uranium as an element, but also the diversity of its isotopes and their properties. These features carry significant implications for both science and practical applications, ranging from energy production to nuclear medicine. The reason radioactivity stands out, especially in elements with short half-lives, is that they undergo decay at a much faster rate. Let's now turn our attention to the most abundant uranium isotope on Earth, uranium-238. This isotope makes up about 99.27% of the uranium on our planet and emits radiation in the form of alpha particles. Its half-life exceeds 4.5 billion years. To put this into perspective, the estimated age of the Earth is around 4.5 billion years, which means that since the formation of our planet, only half of the original uranium-238 has decayed, showcasing its lengthy half-life. Uranium-238 plays a significant role in the dating of rocks. You might be familiar with carbon-14 dating, a method effective for more recent projects since the half-life of carbon-14 is just 5,730 years. For dating much older objects and events, like dinosaurs, we use elements with significantly longer half-lives, such as uranium. But what if an adventurous person stumbled upon a chunk of uranium? What would happen upon touching it? Naturally, finding pure uranium is unlikely since it's usually found in rocks like pitchblende, a black mineral that can contain up to 88% uranium. However, setting aside this hurdle and imagining you found uranium-238 in its purest form, let's explore what would happen if you touched it. If you held a kilogram of pure uranium-238, the first thing to note is that while it emits radiation in the form of alpha particles, these particles have a very low penetration power. This means human skin can act as an effective barrier against them. However, this doesn't make uranium completely safe to handle without precautions, as prolonged exposure or the ingestion and inhalation of uranium particles can be harmful due to its chemical toxicity and radioactive potential. Therefore, while direct contact with a piece of uranium uranium-238 might not result in significant immediate harm, it's crucial to handle such materials with care and proper knowledge of their properties and risks. If you had a kilogram of uranium-238, its radioactive activity would be 12 million disintegrations per second. In other words, this kilogram would be emitting 12 million alpha particles every second. While this figure might seem alarming, the reality is that it translates to a radiation dose approximately 70% of the dose we naturally receive from environmental radiation sources. Surprisingly, the greatest risk from uranium-238 doesn't come from direct contact, but rather if the material is ingested or inhaled. When discussing alpha decay, it's commonly noted that a simple sheet of paper is sufficient to block these particles. Moreover, at a certain distance, the air itself can act as an effective barrier. However, if a source of alpha particles is ingested or inhaled, the situation changes dramatically. By facilitating these particles' entry into the body, you're allowing them to interact directly with your internal tissues. Due to the charge and high mass of alpha particles, this interaction is very intense. For example, inhaling uranium particles puts them in direct contact with the lungs, significantly increasing the received radiation dose, which can lead to far more severe damage. Another crucial point to mention is that the uranium used in nuclear power plants and atomic bombs is not uranium-238, but uranium-235. Uranium-235 is much less abundant in nature and requires an enrichment process to increase its proportion relative to uranium-238. This isotopic difference is vital because uranium-235 has properties that make it fissile, meaning it can sustain a nuclear chain reaction essential for both nuclear energy generation and nuclear weapons. Understanding these distinctions is key to appreciating the different applications and risks associated with the various uranium isotopes. Uranium-235 naturally occurs but makes up only about 0.7% of natural uranium. Despite its scarcity, it is critical for the operation of a nuclear power plant due to a unique characteristic: its efficient capacity for nuclear fission when it absorbs a neutron. The likelihood of uranium-235 absorbing a neutron and thus undergoing fission is approximately 600 times greater than that of uranium-238. This makes uranium-235 the preferred choice for use in nuclear reactors and in the manufacture of nuclear weapons, while uranium-238, though more abundant, is not as effective for these purposes due to its lower probability of undergoing fission under the same conditions. To use uranium in a nuclear power plant, a process known as enrichment is required, which boosts the percentage of uranium-235 relative to uranium-238. A uranium-235 concentration of between 3% and 5% is sufficient for a plant to efficiently generate energy. Moreover, uranium-235 is significantly more radioactive than uranium-238, being approximately 6.3 times more active. Imagine having a kilogram of pure uranium-235. The radiation dose received would be almost 100 times greater than the dose from natural radiation sources. If someone managed to enrich uranium-235 to 100% purity, the primary concern would not just be the radiation but also the legal and security implications, as such material could be used for highly dangerous purposes like manufacturing nuclear weapons. An intriguing fact is that if you had a rock containing natural uranium, which includes both uranium-238 and uranium-235, as well as their decay products, the radiation dose would actually be higher than that of pure uranium. This is because some of the decay products of uranium are more radioactive than uranium itself, and they emit beta and gamma particles, which have a much greater penetration power than alpha particles. This complexity underscores the importance of understanding radioactivity and the risks associated with handling radioactive materials, highlighting the need for strict precautions when dealing with such substances. The interest of Marie and Pierre Curie in pitchblende, a uranium-rich rock, was sparked by a fascinating observation. The rock seemed to emit more radiation than isolated uranium should, suggesting the presence of even more radioactive elements. In 1898, the Curies announced the discovery of two new elements they had isolated from pitchblende. The first, named polonium in honor of Marie's homeland, is part of the uranium decay chain. Later that same year, they announced the discovery of a second element, radium, which is 1.4 million times more radioactive than uranium. These groundbreaking discoveries earned the Curie couple the Nobel Prize in Physics in 1903 for their contributions to the field of radioactivity. Moreover, Marie Curie received another Nobel Prize in 1911, this time in chemistry, for her work in isolating radium. However, it's essential to be realistic about uranium enrichment and handling. In reality, it's highly unlikely, and we hope impossible, for anyone to enrich uranium-235 to 100% purity. If you were to come into contact with uranium enriched to 5%, which is the minimum level used in nuclear power plants, the radiation dose you would receive would be relatively low. This raises an important question. Why then are there such stringent safety measures in nuclear power plants if alpha radiation can be blocked by a simple sheet of paper? The answer lies in the complexity of risk management and the prevention of exposure to different types of radiation, not just alpha, but also beta and gamma, which have a much higher penetration power. The massive concrete walls and detailed safety protocols protect workers and the environment not just from direct radiation, but also from contamination by radioactive particles and potential accidents that could release radioactive materials. It's a precautionary principle that takes into account the health and safety of people and the planet, emphasizing the importance of handling these materials with extreme caution and respect for their potential consequences. The waste left over after nuclear fission, commonly known as radioactive waste or nuclear residue, poses a significant challenge to our society, and for good reason. To better understand, let's revisit the concept of nuclear fission. During fission, a uranium nucleus splits into two smaller nuclei, releasing neutrons and a substantial amount of energy. These smaller nuclei can be of any type, as long as their proton total equals 92, the atomic number of uranium. This leads to a wide variety of possible nuclei combinations, with some being more likely than others. The issue arises because many of these nuclei created through fission are radioactive, often significantly more so than uranium itself. They can emit alpha, beta, and gamma particles of various energies and have half-lives that vary greatly. This means that, unlike uranium-238, which primarily emits low-penetration alpha particles and has a long half-life, these fission products can be extremely hazardous to human health and the environment, even in small quantities. Managing nuclear waste is a complex task, as it involves not just securely storing it to prevent contamination, but also doing so for periods that can span thousands or even millions of years, depending on the material. This requirement for long-term storage and the associated risks make nuclear residue a sensitive issue and a significant challenge. Therefore, while uranium-238 itself may pose a relatively low radiation risk, the story is entirely different for its fission products. They underscore why it's essential to approach nuclear energy and its waste with seriousness and caution. This also explains why it's not advisable, under any circumstances, to be cuddling up with uranium or any other radioactive material. Ensuring safety in handling and storing radioactive materials is crucial to protect human health and the environment. Arguing that the radiation dose from radioactive materials is less than the naturally received radiation does not mitigate the risks associated with additional exposure, especially in the case of uranium. Firstly, obtaining pure uranium would already be a complex task, and, in practice, if you found a rock containing uranium, the radiation dose would be significantly higher than that from isolated uranium. This is due to the various naturally occurring radioactive elements in the rock, as previously discussed with pitchblende and the Curie's discovery of polonium and radium. Furthermore, it's well established that the risk of developing cancer increases proportionally to the dose of ionizing radiation to which a person is exposed. Therefore, deliberately exposing oneself to a radiation dose 70% higher than natural exposure would be a questionable decision. After all, no one would want to voluntarily increase their risk of developing cancer. Beyond the dangers of radiation, there's another concerning aspect regarding the handling of uranium: its chemical toxicity. Like lead, uranium is a heavy metal and, therefore, toxic. While there's natural exposure to uranium through the consumption of food and water, this exposure occurs at very low levels, typically without posing a significant health risk. However, the Centers for Disease Control and Prevention (CDC) sets a maximum acceptable limit for this exposure, indicating that levels above 30 micrograms per liter can be harmful. This limit is established based on studies and scientific evidence aimed at protecting public health, highlighting that, although we can coexist with certain levels of exposure to potentially toxic substances, it's crucial to minimize this exposure whenever possible. Therefore, handling uranium or any other radioactive and toxic material unnecessarily and without proper precautions is not just risky, but also unnecessary, reinforcing the importance of following safe practices and public health recommendations.